Is it all okay? Good. Okay. Great. Thanks for having me. So, where are the slides? The other thing?
The pink one.
Okay. Yeah, I saw it.
Different
Yeah.
desktop. So put this one there.
This one back. Okay.
Yep.
Or should I? Is there something I can do?
Yeah. Go to so that you're not you're mirroring your desktop.
Oh, okay. Yeah.
Settings.
Sorry. Let me figure out how to do that. Great. So thanks for having me. This is joint work with Lisong, Santosh Vampala, and Bo Shi at Georgia Tech. So I'm going to be talking about neural networks, and in particular some lower bounds for training them. But first, the good news. We've all seen over the past several years this wonderful success in machine learning that's been brought about using deep learning techniques. You can play world-class Go. You can classify images more accurately than humans, at least for some sort of narrow tasks. You can drive autonomous vehicles. Really anything you would want to do in machine learning, try some deep learning and maybe it works, at least in practice. So the practical success of deep learning has been phenomenal, but we'd like to understand why, and the formal guarantees have been a little bit lacking. At UChicago, I think there's an unofficial motto. I know it works well in practice, but what about in theory? So without further ado, let's talk about theory. I'm going to be talking about the realizable case where the concept that I'm trying to learn is itself represented exactly by some neural network. Of course, this isn't really a constraint on the sorts of things that I can learn, because neural networks can just about represent anything. But there are some classic lower bounds for learning neural networks or for training them. It's in fact NP hard even if our neural network is tiny, right? 3 threshold neurons. And even in the improper setting where I'm not trying to train a specific 3-neuron neural network to represent the specific other 3-neuron neural network, but I'm allowed to use any network architecture or any approach to learning whatsoever, still under some cryptographic assumptions. For example, this can't be done efficiently, even for small neural networks. Now, of course, these threshold neurons are not something that you would ever use in practice. And the distributions here, well, OK, so the threshold neurons can be approximated maybe by some sigmoid or something. So maybe that's not a severe criticism here. But the distributions that show that these are difficult classes to learn are in some sense unnatural things that we wouldn't think would resemble things that we see in practice, right? On the other hand, even for very nice input distributions, there's a very nice paper by Shamir recently, at least some deep learning algorithms don't work. And what do I mean by a deep learning algorithm? I mean, take a neural network and do some form of stochastic gradient descent with, whatever loss function, whatever regularization scheme, whatever you want to do, as long as you're in some sort of, gradient descent framework for training a neural network. So that's what we know we can't do. in general, most of these hardness assumptions are things that require some assumptions about either the activation units or the distribution, the input distribution, or the specific sort of algorithm that we're using. There are some positive results, on the other hand. We just heard one of them, for example. We can learn linear dynamical systems. That's a linear recurrent neural network. Or we can learn single layer neural networks with ReLU gates, rectified linear units, that have some very strong additional structure. There's a recent paper. And we can also do some learning of neural networks using things that aren't necessarily classic deep learning algorithms, for example, tensor decompositions. For say, small enough neural networks, or under additional assumptions about the neural networks. But what about a neural network like this? We've got Gaussian input, your favorite smooth units, say sigmoid, nonlinear units, not too many of them, and just one layer, a linear output. This is a nice family of functions in some sense. The distribution, input distribution is smooth. My activation units are smooth. Can we get any formal guarantees for this class of functions? Well, you read the title of my talk, so no, you can't. But try. Try using deep learning. Use your favorite network architecture. Whatever activation units, loss function you want to use. Maybe you want to do something fancy with the Hessian. Whatever regularization scheme you want. So the theorem I want to sketch in this talk is that it's not going to work. At least if you're only using a black box function of the input, so you plugged it into TensorFlow and then computed the gradient, or you computed some Hessian somehow, I'll need to define precisely what I mean by a black box function of the input. But anything that would fall into a standard deep learning sort of algorithm is going to fit this picture. You'll either need an unusually large batch size. So you'll need to process that many examples every time you do a gradient update. Or you'll need exponential time. And I should mention, you can actually improve the batch size even further by introducing some parameter of the activation units of the concept to be learned, the true network. I should mention that these networks can in fact be learned efficiently, or at least a variant of them can be learned efficiently. Again, using something that's not necessarily a classic deep learning network algorithm, using tensor decomposition instead of the gradient descent that people use all over the place in practice. Using a little bit of extra information as your input about the density of the input distribution. But we also get lower bounds for this approach. They're just not exponential. On the other hand, there are already exponential lower bounds. I mentioned this earlier. For learning this sort of family of functions in a more restricted class of algorithms, so more of a vanilla stochastic gradient descent where you have a specific loss function and you're not doing anything fancy with the Hessian or anything like that. Though on the other hand, this holds regardless of the batch size, if I understand correctly. It's non-realizable. The functions that are hard to learn here are not exactly this, but they're very similar in spirit. And I should mention also that the specific parameters of this hard family of neural networks are also not particularly important. You can use your favorite activation unit here. You can use whatever nice input distribution you want. You can decrease the number of units here and still get some guarantees. But nevertheless, no matter what approach you try to use in this framework, you're not going to learn it. So let me define more precisely the sorts of algorithms against which our lower bound applies. So pretty much any gradient descent algorithm is going to have the following form. You have some function of your current weights for your learned network. And the labeled examples, so this function here could be the gradient of your loss function. And you estimate the expectation of that function over some labeled examples drawn from the input distribution. And then you use that to update your weights. And our lower bounds apply for any query function you have here, any function where you evaluate the input distribution where you measure the expectation of that function over your input distribution, and where that is your only interaction with the input distribution. So these sorts of algorithms are called statistical query algorithms. And there's been a long line of really rich work on these algorithms. So formally, a statistical query algorithm is one where your interaction with the input distribution, so over labeled examples of your class to be learned, is only through one of these oracles, and not, you're never interacting directly with labeled examples. So you always have some query function, and usually you'll have a tolerance parameter, and what you'll want to do is estimate the expectation of your query function up to some tolerance. So estimate the expectation of the gradient of your loss function up to some tolerance. There's a variant of this oracle. So this is the stat oracle. There's a variant vstat where your tolerance varies with the expectation of the function. And there's a different sort of oracle that has been studied in the literature where your queries, instead of being real valued in some bounded interval, are binary, but your response is guaranteed to be exactly drawn from the distribution and then evaluated. Your function is evaluated on that example. So there's no tolerance here. It's just an honest answer to. Yes?
So in the slide where you had the general form, it was always that you had an n-dimensional product distribution on the input?
Yeah, n-dimensional product distribution, yeah.
The theorem was that one of the lower bounds is that you needed n batch size, yes?
Yeah.
So in practice, we should substitute this with kind of the degrees of freedom in the distribution. And because typically that number isn't going to be so big. So do you believe that the n is the true lower bound, or do you think it should be exponential in n or something like that?
It can't be exponential in n because there are these polynomial time statistical query algorithms.
Then, so this isn't so bad, right?
Well, do you use batch sizes that are? I don't know. In practice, batch sizes tend to be some constant, right? Some reasonable constant. And I think in practice, if I understand correctly, I'm not a practitioner, but if I understand correctly, what people have observed is that some of the power that you get from stochastic gradient descent comes exactly because you're not exactly estimating the gradient, but you're allowed to jump around.
What I'm saying is that, so let's say we have a batch size of 128. So are you thinking that the manifold that the images lie on has dimension higher than 128?
Well,
it's a philosophical point, not a technical one, but I'm just wondering if that lower bound really is that damning.
Okay, well, so there's two answers. One is that I think there are natural problems where the input distribution is in fact high dimensional. I mean, okay, so you're saying close to some low dimensional manifold. But the other answer is that we have, okay, you can improve this batch size up to a parameter of your of the threshold to be learned. So if there's, this corresponds to to sort of to how well you'll see the parameter in a little bit, how sharp your gates are. In the true model that you're learning, right? So if you think that there are sort of sharp phenomena in practice that appear, then maybe it's not unreasonable to expect that this parameter S here is large in nature. But that's a reasonable question. Yeah. So this statistical query framework has been analyzed pretty extensively. It was introduced back in 1993 by Kearns, who gave lower bounds for learning noisy parity with this stat oracle. That was the first of the oracles that I mentioned. The VStat oracle was introduced later to get tighter lower bounds. And this 1-bit oracle where you have your query function is binary and you're guaranteed to get a response actually drawn from the input distribution exactly, but not with any tolerances. The so-called honest oracle was introduced by Qi Yang in 2001. And there's been a lot of successful work giving really nice lower bounds in this framework. And as I mentioned, this is a pretty broad framework. Really, I mean, any variant of gradient descent works here. Tensor decomposition algorithms can be viewed as statistical query algorithms. So if you have some algorithm, I mean, this is a good chance it fits in this framework. So let me give a formal statement of our results then. So the sharpness parameter that I mentioned, for a sigmoid function, it's just, it's measuring how close you are to being a threshold function. So the sigmoid function is in this form. And our theorem is that there is some family of reasonably small neural networks with S-sharp sigmoid units in a single hidden layer, such that any statistical algorithm learning these functions over any log concave input product distribution requires d-queries to stat or vstat with the tolerance parameters tau or 1 over tau squared, or 1 over tau squared queries to the 1-bit oracle. And here tau is 1 over s root n, and the dimension, the d is 2 to the omega. Questions about the statement of the theorem? Yes?
So will you also explain how the statement implies the state of the batches that you made?
Well, okay, so you want to estimate. Okay, so either you're estimating your gradient within this tolerance. How can you guarantee that you're estimating your gradient within this tolerance? Well, by using enough examples, right?
Right, but you get more from stochastic potential. You can get potentially a better estimate if you actually use the true samples. Like you'll get an unbiased, fresh estimate versus the oracle, which might potentially give you something worse, right?
Mm-hmm. Yeah. So the number that you need is, I guess, still polynomial here in
Yeah, I'm
in
just
this
saying
term.
how you go to this sort of this more. How do you infer the statement about the actual stochastic gradient descent? That's.
Yeah. So I guess just generically, if I have one of these functions here that I want to, have, if I know something about its variance, say, and I want to estimate the expectation within some tolerance here, I need a certain number of samples, and the number of samples is going to be
Sure.
polynomial.
Okay, sure. We can take it aside, but basically the stochastic gradient descent potentially gives you potentially stronger than the oracle. So the lower bound is for an adversarial oracle.
Yeah. Oh, I see. Yes.
One will give you unbiased estimate and which might have additional properties.
You're right. You're absolutely right. Yeah.
Exactly the same.
That's true. That's absolutely right. Other questions? Okay, so this, as I mentioned, this sigmoid here isn't really a critical assumption. You can replace this with really any gate that you would want. Say, for example, if you have a monotonically increasing function between 0 to 1 as your activation unit, then you can do the same construction there. Or even more generally, basically, if some affine combination of your activation units is integrable, has finite integral, then you can do this assumption. So in a nutshell, then, nothing about your activation units, nothing about your input distribution is making the problem easier, at least up to these tolerances for statistical query algorithms of this form. So this is in contrast to the sort of lower bounds, the earlier lower bounds for learning neural networks, where the input distributions were very non-smooth, and the activation functions tended to be like thresholds. So let me sketch a little bit about this, about how we prove this. So here's the construction. Take your sigmoid gates, add two of them together, and you get something that looks like this. Some bump function. Add a bunch of these together, and you get something that's vaguely periodic, at least on an interval whose width corresponds to the number of these units that you've stacked next to each other. And the proximity to being, how close it is, how far it is from being actually periodic on this interval is something that's improving with the number of units that you stitch together here. So for any closeness to being periodic here, and for any width of an interval on which you want this to be periodic, you can add up enough of these pairs of sigmoid gates to make this close to periodic. So this is the basic function that is used. Here's an example of the construction with ReLU gates instead of sigmoids. Take two of them, you get something that's monotonic and bounded. Add two of those together, and you get something that is integrable, and stack a bunch of them next to each other, and you get something periodic. So here's 4 ReLU units per period of this close to periodic function here. So use your activation units to construct this function. Now, what are the weights of the neural network? Well, for any subset of your inputs of size 1/2, just evaluate this almost periodic function on the sum of those inputs. So that's pretty straightforward. So I have this periodic function here that's an affine combination of my sigmoid units or ReLUs or whatever, and each of them is being evaluated on the same sum of half of the inputs. So there's 2 to the omega n such functions as I let the subset vary. You might say, hey, this is rank 1. I don't like that, but you can add a little bit of noise and make it have polynomial condition number, the weight matrix. So this is the construction. This is the explicit family of neural networks that is difficult to learn with a statistical query algorithm. So how do we analyze statistical query algorithms? So the classic tool has been this concept of statistical dimension. Here's one version of it. The statistical dimension with average correlation gamma of a family of functions C over input distribution D is the dimension is D if for every D fraction of your functions, the average correlation, so you average the pairwise correlations of your functions in that not too small subset, that average correlation is small. So any not too large subset of your functions is has small correlation. So this has been used for mostly for like Boolean functions. We're talking about real valued functions here, so we need a modification. I think this is Vitaly Feldman's idea. Instead of, so it's a slightly more complex notion of statistical dimension. Let me first say what a non-smooth mollifier is. It's a function with bounded support, say on some epsilon interval and finite integral. And I write chi y for this mollifier shifted by y. Instead of having average correlation of my functions being small for any large subset, I say the epsilon statistical dimension is D if any 1 over D fraction of my functions has not just small average correlation, but for any real number y, the mollifier shifted at y of my function, this family of functions here, composed with one of these mollifiers, has small average correlation. Okay, that's a mouthful. What does that mean? Here's a picture that makes it easier to understand. So if I have a pair of functions from this family of functions here and some y here, for a random pair of functions, even in a somewhat small subset, a 1 over D subset of the total, if I compose these functions with some mollifier, what does that do? It concentrates the mass where the output is close to this y value. Even these things are poorly correlated. Okay. So, and the theorem then is that if this condition holds for your family of functions, then you get exactly this sort of guarantee for the stat and vstat oracles. Learning them with tolerance depending on gamma, your average correlation requires number of queries corresponding to the dimension. So the number of the size of the subset. And for this honest oracle, you only get the smaller of the two. Okay. So it suffices to analyze this statistical dimension. Any questions about the statement of this? It's a little technical. Right. So it's the punchline is that it's enough if on average my functions have small correlation, even if I just look at the functions in the neighborhood of some particular output value. Okay, so how do we show something like that? So take a pair of subsets of your input coordinates. So subsets of size, say 1/2, each such subset corresponds to one of the functions in our class. Suppose that their differences are large, so that happens generically. I mean, it happens for most pairs of subsets. So the claim to show that the statistical dimension is large is that the covariances of these functions here are bounded, are small. So in particular, the smaller than something decreasing with n in the denominator. So in fact, this is going to work for, I'm allowed to choose the mollifier here for the lemma. It's going to work for any Lipschitz mollifier here. So let G be the functions that I'm trying to understand their covariance. So chi of y composed with this periodic function. So this f, these terms here are exactly G evaluated at two different sums of input variables. So this is exactly the form of the expression that I want to bound. And the key point, of course, is that these two here are, these two quantities here are independent after I condition on the intersection, the variables that they have in common. And so all I need to do is to bound this covariance here is just for each one of these, conditioning on every possible value that the intersection might take, show that even conditioned on that value, the expectation is still small for each of these.
John, so remember correctly, also in the paper by Shamir, he also analyzes basically correlation between fully periodic functions.
Mm-hmm. Yeah.
In this case, and there he gets that the correlation is exponentially small. So the question is like, why? What is the difference? Sort of, why do you get relatively large correlations? I mean, much larger than the exponentially small in the fully periodic case.
Mm-hmm. I mean, his had a very special form, right?
I mean, but it's a special form, but it's the same sort of periodic functions on the product distribution, right?
Mm-hmm.
Or I mean, his is like Gaussian, something like this, some Fourier assumptions like that.
Yeah. Yeah, it's not the input distribution. That's the.
Yeah, so what is the I mean, he has like a general just assumption of periodicity, and as far as I remember, integrable functions, integrable periodic functions.
Mm-hmm.
So yeah. So why do you end up with large correlations as opposed to exponentially small ones?
Yeah, I think this is the correct bound.
I have a question.
Yeah.
Wasn't the Shidov-Short-Shamir construction on the real line?
Yeah.
Univariate?
Sure.
And this is n-dimensional.
No. His dimension. No, it's n-dimensional, composed with one-dimensional periodic function.
Oh, Shamir's.
Well, it's a two-author paper. It's not a.
Well, so there are two papers.
Oh,
There's one on Shamir, and then there is a three-author paper. Anyway, it's okay. We can look into it later.
Yeah. So. Yeah. In order to get even a polynomial bound here, you already need a polynomial number of gates.
So you're saying it just because you have a limited number of gates?
Well, certainly that would be one way where you're getting lost, but still there would be a number of gates. That's not the bottleneck in the analysis. The bottleneck is exactly analyzing this. I have some periodic function, and I want to know what happens compared to its expectation if I shift it by a little bit over some input distribution.
So do you know that this is true kind of numerically, or that these correlations will be large, or this is the best?
Well, it's the best estimate that I have, and I think at least intuitively it makes sense to me. Right, so
We think it's type.
I think it's okay.
Yeah. Okay. So So as I was just saying, of course, okay, so we have this thing that's nearly periodic. Okay, you pay some penalty that depends on the number of units you use to approximate this by something that's truly periodic, using the fact that this modifier that chi here was actually Lipschitz. You can do that for any Lipschitz function. So the real question then is what happens now that I have this actually periodic function. I shift it by some arbitrary amount, and what has happened to its expectation over this sort of input distribution here. Okay, I can assume since it's periodic that my shift here is less smaller than my period. So I have two things that are close here, but they're only as close as the period, right? And now I've shifted something. Okay, so this term here is like the expectation of my periodic function under one density. This term here is like the expectation of my periodic function under some other slightly shifted density. What is the difference between the expectation of these two values? I don't think it's exponentially small.
I think that if you look at the infinite range, I think it's exponentially small. For Gaussian distribution, it would be exponential.
It could be, yeah. Let's talk about it offline. Yeah. As I say, I would be surprised also because we have upper bounds, right? We have algorithms, statistical query algorithms, that work for these.
But you mentioned some assumptions. But okay, so
Okay,
I don't know.
yeah. Okay. So let me mention that. Okay, so these aren't just abstract lower bounds. They're actually, I mean, in practice, you can't learn these functions, at least not with deep learning algorithms, right? So you were asking me, before, is this assumption on the is this batch size actually prohibitive? Well, I mean, even with so these plots here are the best over a number of different architectures, a number of different gates used in the model architecture, different batch sizes, trying to learn exactly these functions, this function family with sigmoid units, and after some point, depending on S and the input dimension, the training error that you get is about what you would get from just a constant function approximating these. So it's in fact, actually in practice you can't learn this. So there's still a lot that we'd like to understand here. When we got into this work, we were actually hoping for a positive result here, that some class of neural networks, not too large with nice gates and input distribution would be, in fact, learnable with usual gradient descent. But so maybe there's some concept of genericity on the weight matrix that does make that possible. Maybe these weight matrices are just nasty ones, though we've done some experiments that suggest that even for reasonable concepts here, you're going to run into problems in practice. Yeah, I guess as some of you have been asking, yeah, it'd be nice to lower these sensitivity bounds. It's a little bit unsatisfying that they're only polynomial. So possibly, I don't know, with greater depth, that would be possible. Or maybe a tighter analysis. Okay. Any questions?